So alternating current basically is a product of, you know, sort of. Hold on a second, please. Hello. Yes. Yes, Maz. उसको भी नहीं ऐड करना. Mm-mm. I'll let you know. Okay, I love this. So basically, alternating current comes from, that, like we have learned, through induced EMF, because um, when you move the magnet like towards or away from it, away from a coil, it basically induces the current. So that comes from induced EMF. So what you're going to understand is that there are three types of waves that can be generated, right? The first one is the sinusoidal wave. That's the sine wave, basically. Then the second one is the pulsating or rectangular wave. And the third one could be the sawtooth or flyback wave. Okay, like that. In fact, why am I even writing wave? I should write voltage. I'm sorry if you had to correct it. The same thing, but I want to, be very specific here. So now, here you go. And here you go. So you see two types of these. And you'll see one type of this. And about the same as this one. Okay, so there has to be an app that makes graphs. I hate this app for this reason. Okay, now, so sinusoidal could be a sine wave sort of thing, like this, right? And it could be like a cosine wave, like this. Rectangular waves are like pulsating ones, like you see in sort of like this, right? And the sawtooth of flyback, basically, just don't get very scared of it. It's just like this. Okay, like that. Now, why do we call these alternating current or wave? It's because, just note that they're alternating because polarity, which is basically their positive and negative sometimes, is changing for all of them, right? So remember that when we're looking at them, we simply,
Please show rectangular voltage again.
yeah, okay, you can take it. I'm sorry, you can draw this. Okay, done, Saman? Who's not
Yes, sir.
here yet? Couple of people missing, right? Let me see. is missing. Ramen is missing. And Rafi. Oh crap. Okay. So we simply cannot take average because it would turn out to be 0, because if polarity means that, of course, if once it was 5 volts and then it was negative 5, so if you take the mean, it will be 0. 5 minus 5 is 0, divided by 2 is 0. However, in order to calculate the mean current, we use root mean square, and that's RMS, if you guys remember that, right? You guys know that from the ideal gases? So we've done RMS speed. Now we learn how to find RMS voltage or current or power, whatever, right? So let's look at this now. So RMS is root mean square for alternating voltage or current. Okay. So when you draw a wave, right? Like suppose a wave like this. Here you are looking at time. Here you have voltage in volts, that's in seconds. So this part where you see the maximum voltage right here, you would call it as V naught, because that's the maximum, right? What I want you to understand is, and that's very important, because from this point, this whole thing is basically half cycle of the alternating current voltage, and when you combine it with this one, so this is a full cycle of one wave. Do you guys understand this, right? Now, because it is a sort of a sine wave that's basically oscillatory in this condition, so the general equation of this would be V equals to V naught sine of omega t. We've learned this in oscillation. And to further, derive this, we can even do V equals to V naught sine of omega is 2 pi f, and there's t always like that. So we can always find the voltage V at any point if we have, like, this is the t, here is the independent variable, which means that if I want to find time or the voltage at this point, at this time, okay, that would be too much, this one. So I would go up, I would check what is the voltage right here, like that, right? And according to that time, this would be the dependent variable. And you can know because V naught is a constant, because the peak value will always be the peak value. The frequency will always be the frequency because the wave has a time period that's fixed. The only variable, the independent, is the time, because at a certain time when you pick and choose that, it would give you a particular voltage depending on that by using this equation or by using the graph. Alright, if you have any questions, please let me know here. Okay. Now, so now we are going to, look at how basically we can compare a alternating voltage with a direct voltage, right? So we need to understand that it is a steady state direct current equivalent of voltage or current which, when connected to a resistor, produces heat at the same rate as the heat produced by the alternating waveform if connected to the same resistor. Now let me tell you what it basically means. So let's suppose that we have one circuit that we built with voltage that is alternating, and by the way, alternating voltage has a symbol of its own, so let's just draw the symbol instead. Let's move it here. The symbol is like a wave. Okay, so this is the symbol, and now we have connected it to a resistor which is 120 kilo ohms, like that. And similarly, we also have a DC. DC is like plus minus only voltage supplied to the same resistor. Suppose 120 kilo ohm. Similar circuit, right? Now the issue with this is that because if I draw the curve of the voltage supplied to this, what you guys need to understand is that DC means that if the voltage was 220, this was 220 volts. So 220 means that the resistor is going to get a constant supply of 220 volts. Right? This is what DC means. Throughout the time, okay? But that is not true for AC, because if you want to give an equivalent supply, I just want to tell you that the only way you can find that is by using this formula that we're going to derive later as well. That the voltage you need will be equal to the peak voltage over root of 2. We're going to do this. So this is later, don't worry. So this is the voltage. This is the peak voltage, and that's just under 2. which means that if I want to find what will be the equivalent voltage that I need to put on AC to get 220 as an average would be 220 times root of 2, and if you find this is going to be 311.1 volts. So if you draw the curve, now the curve is going to look like this because it's alternating. So you need to understand that in AC voltage, at least you need to give 311.1 volts if you want an equivalent of 220 volts as DC. Do you guys understand what I've just done?
So can you do the last part again?
Yes. So what I'm saying is, Suman, that you are supplying 220 volts DC to, any resistor. But in AC, if you look at it, it's not basically a straight line. It's going up and it's going down and then negative and then up and down like that, right?
Yes, sir.
So every single time, like here, if I say, okay, this is 1, this is 2, and this is third. So every second, the resistor is getting the same amount of voltage, right?
Yes, sir.
But if I say this is 1, and this is 2, this is 3, this is 4, is the resistor getting the same voltage every second? I don't think so, right?
No, sir.
So what I'm saying is that in order to give it equivalent voltage, you need to use this formula. Where in AC, the peak voltage that you need would be, actually we need 220 equivalent, so 220 needs to be multiplied with under root 2, and this peak voltage shows that this is the amount of peak voltage that we need to supply, which is like this one in AC is equivalent to 220 volts in DC. And that is the reason you might have heard that, okay, DC inverters or fridge or TV, whatever, they basically are power savers, right? Because they can deliver the same amount of energy in by using less voltage. Do you get my point now?
Yes, sir.
Aman, do you understand this? Hasanati, Kartika?
Yes, sir.
So that is the reason new trend people are using all these DC appliances. They're like, eh? Okay. So they're like using it and they're like, yeah, let's put on those because they know, in fact, it is proven that it costs less because you're using less energy altogether. All right. Now, not just this one, right? We also need to learn how to calculate root mean square values of a square wave, right? So we're going to do that, rectangular square wave. So I hope you guys have written it. I can just now go forward. Okay. So, how to calculate the RMS values by just looking at the wave, right? So first of all, we're going to look at the square wave. And then we're going to learn about the sinusoidal one. So this involves a bit of method. So I just want you guys to follow this. And hopefully you will be able to learn. It's not something difficult at all. So suppose the wave is given like that. And then like this. Okay. So this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8, and 9, right? So it's given like that. Here you have voltage given. This side is 2.5, and probably I made a mistake here, so I'm going to correct that. You don't have to. I just need to do it on my own, but it's okay. Let's put -1 here. Alright, now so they have given you the voltages on either side, and they have also given you the time on this side in seconds. So let's follow the steps, right? So first step, when you see a rectangular wave, is that you basically isolate one time period. In this case, you have it as 3 seconds. Because you see, this whole section, if I just, this is one wave that you see. Everybody agrees, right? Okay. Okay. The next thing you're going to do is in step 2, you say, okay, square all the values over this time period. Okay. Now, if I square this, you don't have to do this. I'm just showing you what it would look like. So if I square 2.5, so I'm now doing v square and t. So if I square this, so that's going to be 6.25. So 2.5 square is 6.25. So it means this value will be 6.25. And how much time? For how much time? That's actually till 1 second, because it was 2.5 till 1 second. And for the rest of like 2 seconds, which is like 2 and 3, if I square -1, it will become just 1. So it will become like this. So the wave, basically, I've just squared it and brought it up. Is it clear?
Sir, we only square till 3 seconds, right?
Yeah, just this time period till one wave is there. Understood? Every value, whatever the change is. Do you understand?
Okay, sir.
Now, step 3. The step 3 is that now you take the mean of all square values over this period. Okay, so how do we take mean? So basically you're gonna just simply add them. So 6.25 remained for 1 second, and then plus 1 remained for 2 seconds. So we're basically taking the mean. Or you can do 1 plus 1, 6.25 plus 1 plus, because there are 3 values, right? Like 6.21, this, and then this, and this. So it's the same thing. Divided by, basically there are 3 values. So 3 equals to, this will be 2.75. If you don't understand what I've done, basically I've done it for each second. So in the first second, it was 6.25. In the second second, it was +1, and the second second was +1, and then I've divided by 3 like that. So every second I've taken the voltage. Is it clear? So it's up to you. You can take the area or you can do this. It's the same thing. Now, the last step, when you're done with the mean, would be that you take root the answer of step 3 to obtain RMS value. And now let's do this. You say, okay, 2.75 under root will give you 1.66 volts. And that is basically the RMS voltage. Do you guys understand? If you look at the steps, what I've done, right? RMS basically means you always go from here. So first of all, you square, we squared it, and then what did we do? We took the mean, and then what we did, we took the root. So that's what RMS means. Is it clear? Any questions?
So can you repeat the third step?
Okay, Gatika, so what is the value between 0 and 1?
6.25.
Okay. What is the value between 1 and 2? So that's total 3 seconds, right?
Yeah. 1.
1. Okay, let me write it this way. You're getting confused. Let me write it this way. So their total 3 seconds. In the first second, it was 6.25. In the second second, it was?
1.
In the third second, it was? So now you get the answer. Do you understand?
Yes.
So for every second we have taken the voltage and divided by the number of seconds, that would give you the mean over the time, right? So that's how it is, right? Got my point?
So that 3 is the total number of sections, right?
Yes, that we have developed. Yes, that's correct. Also, the funny thing is, it is also the area. Do you see? So it's not this. It's the same thing. Don't worry about it. Okay. Now, everything is clear. Should I give you a question now? I hope you guys will do it. Let's do a question then. So the question suggests, it says calculate the root mean square voltage value. Okay. And now they've given you a pretty strange kind of graph. So here this is -2, and then it goes here, and then this is 2, and then it goes to double of this where it is 4, and okay, I should not have done that. Okay, let me make it 4 here, and then they have 4 stays till 6 second, and then it goes to 12 and stays there for about 12 seconds, and now it's like this, and then it repeats itself. Like that. Okay, this is 14, this is 18, and so on. This is voltage, this time. Now Gatika, the way I did it first, right? You do that, otherwise you will have so many variables, you will be like stuck. Okay, so you just find the area, that would be fine. Okay, now I want you guys to focus on this, and let's try and do this. Okay, I just want a number at the end. Please start this.
So how did you do it at first?
In the first step,
No, I mean in step 3, what you did before.
in step 3 I was like, I said, okay, this is the sort of thing, right? So 6.25 remains for 1 second, right? The whole 1 second, and then 1 remains for 2 seconds, and then I divide by the total time. Voila. Do you get my point?
Yes.
So you do this because for this one you have to make then 12 values, and 12 values will be 2 too difficult for you. So don't do that.
So sir, we take the area.
Sort of, yeah, of course.
So how would we have 12 values?
Because there are 12 seconds in the whole wave.
Yes sir, but it's only staying at them at 3, right?
Yeah, but then if in the way Agatika asked me, you have to find for each second there will be a value, right? So then you have to add 12 different values and divide by 12. If you're not following the one I did earlier, you know. Okay, we'll do explain it, don't worry. So in about 1 minute, I believe, you got to rejoin the class, all right? And then I start explaining this. Aman, are you getting everything?
Yeah, sir.
Okay. That's good. That's very good. The first thing you guys need to do is you gotta basically, um, highlight the area that you're looking at because that's one wave. Okay, look at that only first. Okay, you have 1.5 second now, 1.5 minute.
Done sir.
Done. Okay.
No sir, I just
Okay. No worries. Okay. So now let me do it for you, okay?
So what's the answer?
Answer has to be 8.83 volts. You got the answer, correct?
No.
Okay, that's not good.
I
Okay,
put 18. I don't know.
18,
किसका आंसर?
the final answer has to be 8.83.
So I got 8.9.
8.9. Okay, let's see. So the first thing you guys need to understand, you're going to identify the part, right? So this is like this one, and this one, and this whole thing is basically the whole one wave, right? Now what you're going to do, if I were you, I would not even try to make the graph, okay? Because I just learned it, but you could do that, it's fine. I'll show you the graph as well if you want to square it up. So the first value that we have is -2. So I'm gonna first square. So basically step 1 was step 2. We'll start from step 2. Square everything. So we're going to take square. This is going to be 4. And then the next point was 4. So I'm going to square 4. This is going to be 16. And then I'm going to square 12. And that's going to be 144. So there are only 3 changes here, right? You guys understand this? Then step 3 was to take the mean. And how do we take the mean? So check this out. 2, which is the square of 2 is 4. How many seconds did it last for? Who's going to tell me?
So 2 seconds.
2 seconds, right? Then plus the next value was 16. How many seconds that lasted for?
Oh, okay, I got a mistake.
2
Yes,
to
sir.
6, that is 4. Do you guys understand this? And how many seconds 144 last for? 6 to 12, that's 6. And then what is the total time that this whole wave was there? 12. So that's the mean, which is basically 78 volt square. Is it clear, everybody? And step 3
Yes, sir.
was basically taking the root. And that's pretty simple. You just take the root. So by taking the root, you're going to get 8.83. And this is the RMS voltage, which is 8.83 volts. All right, Aman and Gatika, do you guys also understand this now?
Yes, sir.
Okay.
So in step 3, you told me we divided by the number of sections, right?
I divided by the total time from here till here. That's where one whole wave lasts for, right? That's how much it lasts for.
So my calculation was correct. I divided it by 3 because there were 3 sections.
No, 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 not the sections. It's total time that you're gonna divide it
Now
for.
I get it.
All right. Now, even if you get confused, right? You're like, okay, oh no, I can't do this. And then what you're gonna do is just make v square graph. And if you make the v square graph, just find the area under the graph, and that would also give you like area under the graph divided by the total time. So it will be like 4, and then it will be like 16, and then it will be like okay.
So can you show the method with the graph?
Yeah. Check this out. 4 into 2. What is this? 16 into 4. What is
4
this?
into 16.
144 into 6 and divide by the total time 12. Get the same thing, right? So it's just that the graph takes a bit more longer, and I don't really agree with this because it's good to do smart work sometimes, don't you think so? Now, before this whole thing gets overwhelming, we're gonna stop right here, okay? And I hope everything is clear now. In the next class, we're going to continue with how RMS value of a sinusoidal wave can be taken, okay? All right.
Okay, sir.
Okay. So I'm gonna see you people in the next class then. Have a nice day. I mean the weekend. Probably on Saturday, I think I will take an extra class for the worksheets of capacitance and what else have I given? Magnetism. So I'll let you know. Okay.